Hello. The fuck? No. Hey guys, I guess I am online. Just give me a second because it's the first time that I'm using OBS to stream. Actually, where is the live chat? My gosh, I even forgot what I want to do. Yeah, I want to change the snapshot, but I think I can't anymore. Oh shit. Okay. I guess I'm online. Let me check. On YouTube on my phone. Oh, yeah, looks like I am waiting. And we should be live. Okay, all right. I wanted to remove the Venice Lab logo from over my face. Yeah, but I don't think I can do it right now. Let me see. Tags. Yeah, now it's not gonna be the time. So yeah, guys. So today I'm gonna start a new series of videos. Let me see on my phone because I'm waiting for Vince. It's kind of should be working. I have no idea what I need to do. Enable live chat. Save. It says that I am live. Please, someone, if I am actually live. Yep, I guess so. Now we are. Please, someone, if I am actually live. Yeah. Okay, so I am actually live. Yeah, there's a lot of delay. Not sure if it's my connection or OBS encoder. I'm using NV encoder. Should be working. So all right, there is if is there. The stream's current bitrate is higher than the recommended bitrate. Recommend that you use stream bitrate of 4500. Okay, so let's see if I can fix that. Video adopt, it's gonna let me. So 4,500 apply. Okay. Not sure if it's gonna work. If not, I can just, I guess, stop. Open widget. String status excellent. I guess it's working right now. Yep. Yeah, it's a little bit delayed. I can see here on my phone, but let's just start over. Okay, guys. So sorry, it's just like my first time using OBS. The last live stream that I did, I used like YouTube web interface. So today I'm gonna be I'm gonna be working on OSMU control board. I have been already working on this board and this project for a while. And for you that are not aware, OSMU is a source measure unit project, and where we came up a couple of guys, and this was an initiative from Marco Raps, and so it's basically a group of people that are together trying to solve a big problem. That is not that is a problem that everyone on a daily life has, but we were being very how can I put optimistic in terms of the specifications we want for our SMU. So since we decided we're gonna make an SMU, we're gonna do it right with all the specs that we dream of. So yeah, so we have been working like for I think over a year already, and but we didn't progress too much until now. But I guess now we're starting to get traction again on this project, and I am personally working on the control module. We have many parts on this project, and the control module is basically responsible for the communication with the operating system, where you can control, or the UI. And this communication is made by EtherCAT. And the reason that we are using EtherCAT is because we want to have a real-time high-performance communication bus with distributed clock to synchronize between different channels. This is a modular approach. So each channel on the SMU has its own fully feature modules for like power amplifier, like signal acquisition, processing, and communication with the EtherCAT itself. So this is something that we have been discussing this architecture for a while, and the idea is to make OSMU as flexible as possible. So if people want, for example, to downgrade the specifications to have a more like cost-effective, they could change a few modules. And this way, yeah, you can do whatever you want, and we are making a way that is very flexible to attend different people's needs. So yeah, so I decided to make this live stream because yeah, those PCB designs, they take a lot of effort, and I think like making this live stream, I can share with you guys something that I'm actually working on my free time, because yeah, this is not a commercial project. This is something that we are doing because we would like to have it. And so yeah, so I have a few things to work together. I would like to complete the EtherCAT module today, like not exactly module, but the circuit of the EtherCAT. So this is the LAN 9252 microchip EtherCAT slave ASIC. And as you can see, I already start like designing here this region of the board. And now I need to add some isolation between the communication here and the microcontroller. The reason that I need isolation is because each one of the channels is floating, so we can't just have like an Ethernet cable running through the different channels without proper isolation. So yeah, I needed to add this isolation. I also gonna add some RJ45 here on this board, on this part here where the region is right now, to create the communication between the different channels. Yeah, so it's a lot of work, and I also would like to work on the ADC today as well. We made a change this week about the ADC. So this is gonna be our newest ADC. It's like a newest launch from Analog Devices is the AD7134. It's basically a 4-channel ADC with 24 bits of resolution at like 1.5 megasamples per second. So it's a per high-end ADC, but it has like a lot of power rails. Like it has like 1.8 volts. It has 5 volts. I'm probably gonna use 3.3 as well. So yeah, I'm gonna need you to create like the LDOs or DC converters to feed this beast here. And yeah, this is like already a lot of work for today. So yeah, so let's start here on the EtherCAT. So this is the schematic that I have right now. And this schematic is actually based on a microchip reference design for the LAN 9252. And I just needed to adapt here a few things. So for example, those ports here, they're gonna go away because I don't need them anymore. And I'm gonna place the connector directly here. So let me go on my correct library here and find, I don't remember exactly what was the name for the connector. So I'm gonna need you to go through here all the components. This is not run. No, let me see this one. No, this is isolation transformer, transistors. Where is it? Miss test point, fiducial. No. I basically imported from microchip the component library because yeah, I didn't want to create all the, yeah, I see con here. So this is one, yeah, I found it. So this is what we needed. So we need 2 of those. I guess the string is quite empty right now. I can see one concurrent viewer. I'm not sure who is this concurrent viewer because it's not sending any message. So if if you're the viewer that is watching, send a hello to me in the chat so I'm sure that someone is actually watching this and I'm not just talking to the wall. Anyways, I hope that people are gonna watch this in the future. This probably is gonna be a very long live stream, so don't expect that this is gonna be finished so soon. Would be naive from your part, but yeah. Anyways, so I guess this is what I have for now. Almost sure that I'm gonna need some inductors here, but for now I'm just connecting here. My grids on this project is like, yeah, they are not working so well. Like kind of like in using the same component, and this component is really not aligning. As you can see here, like it's like jumping halfway the grid, and I hate when you're using components from other people's because there's always some issue on this regard. So I guess I'm go con 1858. So let's go to the library, schematic library. And I'm gonna try to, yeah, it's on the grid. So let me just positioning here in the middle. Give it a refresh. ECAT here. Let's delete this port and try to place it again. Yeah, you see now it works. Okay, now we annotate those two components. I like to work on an interactive way, meaning I always like to, place components. Then I go in the PCB and I come here. I bring in my changes. Yeah, automatically create. Yeah, I don't care. Go away. Cool. So yeah, those are big connectors. So what I'm thinking to do here, I want to give them some space. Okay, so J5 goes so what I want to do here is first do this, because then I let I'm gonna remove the ZPROM from here. And I wanna delete those traces here. You come this side. And I'm probably gonna extend the board on the connector's direction. Okay, so this goes here, and this guy goes here. Let me define my grid, 1 millimeter. Yeah. Yeah, you go here. Go here. Okay, and this ZPROM, for now I'm just gonna put there. And this is gonna be an isolate circuit. So what I'm gonna do here is I'm gonna tight those connector as much as possible. Let me bring this room here. I like to keep my region tight. Okay, so this region is gonna be in entirely like isolated range. So I guess what I'm gonna do is something like so, because then I have, yeah, I have a lot of space for the microcontroller. Okay, you come here, you come here, you come here. Hello, Mako. Yeah, so I'm glad that you are here. Let's make this OSMU work. Okay, so like so, yeah, actually I don't need you to push too much because yeah, I just care about the connector pads. Yeah, like so. Now I bring it this board. Yeah, actually I'm wrong because I don't want to do this way. I want to actually short um, this thing here. And the reason for that is we're gonna have components under this board here. Let me give you a show. So if I come here and show, so we have these IDC connectors here. They are tall. They are like with the mating one. They are like 15 millimeters. But like so, we have our base board under this board. And the reason that I want to have this cut out because if we want to have some large capacitors, for example, I want to have as much space as possible. So I don't need to make this board square. And since here I'm definitely not gonna need all this extra space here, so I'm already gonna make a cutout here so I can optimize vertical space for the lowest board. So if we have some really tall components, it's not gonna interfere. This is actually something that I'm gonna keep here. So let's see. Select my downlight. Go away. I love the sun. Like so. And I love my roundy corners. Makes the board so pretty. Why you are not snapping? Wow. Fucking audio. Those things makes me crazy. Just snap audio as I command. This line we don't need anymore. And yeah, so, and this is not final. If I need more space afterwards, I am totally happy to give it more space. Oh, I see. My curve wasn't exactly 90 degrees. Now it is. Let's grab this trace and we bring it here. Yeah, actually, I think I'm gonna bring a little bit lower. Because like this IDC connectors here, here in the top and the bottom, they are kind of like they're lost space because like this board is gonna be like 4 layers, and we have like power plane and ground plane over the middle layers. So I basically have 2 usable layers, and like yeah, I need to route these 2 rows. So because we are constrained to 4 layers and trying to keep the connectors region clean, so I can route easily. So I don't want to keep connectors there. So this like this left and right side here, it's basically open space that I have for free. So let's optimize a little bit more. If I need more space afterwards, I can just, yeah, so like so. Yeah, actually I'm being stupid because I can actually come over here. And this guy can come on like so. Excellent excellent place. Now we extend this one. Just so guys know, those 2 horizontal lines here, they are basically the maximum height that we have for the module. So I'm trying to optimize, like using the maximum as possible of my height and optimize as much as possible of my width. Because yeah, we have like a heat sink on the left side, and we have power supply on the right side. So as much like and narrow I can make the board is better. Why don't you stay? Or I need, yeah. 90 degrees, yeah. I love to roll boards, but I think like making schematics is pretty boring. Okay, almost there. Design, board shape, define from select objects. Great. So now we have a new board shape for our OSMU controller. And now I can create a keep out zone. So I was actually planning to share the crystal with the microcontroller, make them both work at 25 megahertz. But then I remembered that, hello, hello, ship guy. Sorry, I was distracted with the PCB. I didn't see your message. Yeah, so I was thinking to share the crystal because, yeah, it's like half a buck cheaper to share the same crystal since we can use the same frequency. But then I remembered that I actually wanted to have a centralized clock for a couple of reasons. First, we can synchronize basically the clock. And of course, like the main synchronization is going to happen by the EtherCAT distributed clock. But yeah, it's always nice to synchronize it. And the second, if we decided to go with the power supply at 1 megahertz to synchronize your sample rate with the power supply, so we can avoid the switching noise, all the channels must be synchronized with the power supply. So my idea is to have like a shared oscillator, and then if you people want to go fancy, they can use, for example, temperature controlled oscillators. I have one here that I'm planning to use for OSMU. Then it's very easy because we synchronize the power supply with this clock, and also all the channels with an optocoupler or anything like this. And also there's a second reason, that is we can use an external clock source. So yeah, so we can use an external clock source, and then we place this capability on OSMU as well, that I think it's pretty standard for instrumentation. So and this is only possible if actually like the microcontroller, the ADC is actually sharing the clock and not sharing with the LAN 9252. And since now I'm adding the isolation between it and the microcontroller, then yeah, it's one more delay. So no thanks. So let's keep out of it. One thing that I want to do is remove those UFL connectors, because yeah, it's really not gonna be useful for us. And what I'm gonna place in their place is our test points. So let's put some test points on the sync signals. They are very important because yeah, our distributed clock depends on it. So annotate quietly, yes. And now we bring our test points. Import changes. Yeah. Yes. Continue. Execute changes. Cool. So now we have 2 additional, 1 test point here, 1 test point there. So cute test points. Hello, LTLKLR gamer. Hi. Let's design OSMU control board with me, because I have a ton of schematic to do, and schematic is super boring. I love to write PCBs, but I hate to do schematics. So yeah, so let's make this puppy work. And okay, so I have a few. I don't wanna delete entirely this traces here, because yeah, I already made the routing with the vials for the differential pair. So I'm just gonna remove a few of the older traces. Hey guys, by the way, since we have a few viewers, yeah, so we have a designing context on going right now on OSMU. We need to basically design the analog front end. So current and voltage measurement, and this front end is what's gonna interface with your DAC and ADC on this board. So we need to do signal conditioning. So we came up with this idea of a design contest on OSMU, and basically we have some prize for who wants to participate, and the deadline is 1 month. So if you are interested on it, well, if you're not on Marcus Reps server where we publish it, I'm gonna ask people actually to post on the forum as well. So if you have an interest, please post on the live chat. And yeah, it's gonna be a very nice contest, and we are excited to see ideas that people come with. And by the way, we're looking for collaborators on OSMU. It's, as I said in the beginning, is a very ambitious project. So we are trying to solve like hard problems. So we are expecting to have 6.5 digits of resolution on OSMU, and like it's not only gonna be a DC SMU. So this is gonna be a totally DC to 100 kilohertz AC SMU, and we are actually capturing at 1 megasample per second. So we really want to have very sharp slew rates. And yeah, so it's a lot of challenge. So we are working on the control model on basically that makes the signal synthesis and capture right now. It's what I'm doing here with you guys, signal acquisition and synthesis. We also have people working on the power amplifier, but we don't have anyone actively working on the analog front end. So this is the reason that we came up with this design contest, because yeah, we wanted to stimulate and give some prizes to people that come with nice ideas how we can leverage the data acquisition. So as I said in the beginning, we have a pretty high-end ADC here, is the AD7134 ADC. It's a 4-channel ADC that can make up to 1.5 megasamples per second at 24 bits of heart resolution. And 2 of those channels, one is for real-time current monitoring, second channel voltage monitoring, and we have 2 extra channels. And those extra channels we can make like very interesting applications. So for example, we can have a Peltier controller, temperature controller, and use those 2 extra channels to actually have a PD controller and to measure the low side or the high side of a Peltier. So we can control the SMU with multiple input variables. So it's going to be a very flexible instrument even for normal data acquisition. So yeah, so we are really looking to ideas how we can leverage those extra channels, and how we are going to make the range is switching between the channels, because the issue that we have right now is that basically our microcontroller is closing the loop in terms of current control and voltage control. So we can simply interrupt, you know, the data acquisition, or so it needs to be faster. That is not actually gonna interrupt the acquisition. And yeah, so there are many ways to do it. We could use PGA, programmable op amps, or we can use like range switching, but they need to be very fast. So and synchronize it. So there are many ways that we can change ranges. And remember that the SMU is an instrument that's gonna measure from micro, or I don't know, pico amps to a couple of amps. So we're gonna have a very wide range to acquire data. And in the same thing for volts, we can be working with millivolts and with like a lot of volts. So as much like performatic the front end will be, it's gonna be best for the project. Anyways, now that I made a pitch regarding the contest, if anyone is curious about it, please check on Marco's Discord server. If you are not there, please leave me a message on this video on the live chat, or when this video finishes on the message channel. At that, I'm gonna follow up with you guys that are interested. And yeah, and I give you access and more information about the contest. Okay, so now let me go back to my schematic. And I have a few resistors to put here. I think I have some chokes as well. I'm gonna keep this for afterwards. I remember that I have some 50 ohms resistors to put here, but I'm gonna focus right now on the isolation. And for isolation, I already have selected a few parts here. And I have this 7761 line up from Texas. Is a very fast digital isolator. So ISO 7761. So let me open the data sheet here. Yeah. And so we're going to use a similar part. The only difference is that, let me go to Texas Instruments website. I have a different window here, guys, so sorry I can't show ISO 7760. Yeah, so it has 60 channels, and depending the ending number is the number of inputs and outputs. So I'm gonna have SCPI communication. So for SCPI, we have clock that comes from the microcontroller, because we are working on the microcontroller is the master here. So clock from the microcontroller. We have MISO, MOSI, and then we have chip select. So the only one that actually is output from the ASIC to the microcontroller is the MISO. No, sorry, master output, slave input. Yeah, is the MISO, and the sync 1 and 2. So we have exactly 5 signals, and we need 3 inputs and 3 outputs. So I just need to find the right codes for the isolator, and it is gonna be the ISO 7763. I have the so we're going to the OSMU library, and I go here on the ISO. I have the 7761. So they only change the pin functionality. So I'm gonna copy and paste this component. So now we duplicate it, and I'm gonna call it ISO 7763. And I have inputs, okay, so 5 and 12. Now this becomes out Alt D. This becomes Alt E. And this is already Alt. And here we turn into input D, input E, and input F. So basically this is the only difference is SSOP 16, so it is the same. So the only difference, and okay, all right. And so let's just edit supplier links, remove here, so we don't have confusion. And now I'm gonna add some references here to I guess is this one, DBF key, because I actually, why the DW is so much expensive. Yeah, I'm gonna place for now the DBF key, Mauser. And I also gonna put DG key. So just making our future builders life is easier if they chose one of those suppliers. They have references for both of them. All right, so now we can come over to our ECAT isolation, and I'm gonna maybe I'm gonna create a so now I need to come here and say compile integrate library, so I can get a refresh. Integrated library. So yeah. So now we have one single isolator with all the signals that we need. Don't use no, I don't usually they don't have the components I need. Is usually exactly the components that I need, they don't. So I just gave away tools annotate quite, yeah. So U7, okay. That's okay. So, okay, so here we have our, let me check one thing on the data sheet. Wide supply range 2.25 to 5.5. I just want to see if there is any constraint of which side. Well, actually not, because I'm gonna be working with 3.3 volts in both of the sides, so I really don't care. So let's just place here anywhere. So now we keep this side here. So we have the our ground, and we have our, let's call and calling, 3.3 from our isolated side. And yeah, so all those parts, I'm gonna remove them from here. I'm gonna place here. This is quad SPI, but I don't need quad SPI for the, so I only need the first 4 pins. So I have here a clock, that is my input. I have a chip select, that is input. And then I have, I'm gonna rename this because this is gonna generate confusion. Actually, I'm gonna rename all of them. I'm gonna call this SCPI CS. I'm gonna call this SCPI clock, SCPI MOSI, master output, and SPI MISO. And I love this nomenclature For example, I hate when we have UseArt or TX and RX because you never know. But this is a transceiver referencing which one of the devices, you know. I like this way because if you know which one is the master, you know what is inputting and what is outputting. Okay, so now we just need an extra 2 here, and those are actually, this is output, this is output, this is input, this is output. And also I'm gonna need to have now my ground and my 3.3 volts because those are the isolated ports. So actually this is, yeah, unspecified. And I'm gonna call this MCU ground and MCU 3.3 VTC. The ISO, no, it's not, because this ISO is, well, this is like nothing in the part that of that circuits, you know, the front end. This is like the EtherCAT is the other side of communications, the digital part. There's nothing related with the analog part. So yeah, those details we are keeping out of the requirements on the. Okay. No, sorry. I was thinking about the designing context. Yeah, is not in designing context exactly. This is the reason that I don't lose my time with design content, because yeah, they never have like the symbols that I need. Anyways, let's bring this thing closer. And around here. So now I have the clock. The clock is here. We have the chip select that is here. We have the S slave in. Oh, I just saw that my naming is actually wrong. So this is gonna be the sync 0. This is gonna be my sync 1. And yeah, and I actually don't need some space there, because I'm gonna have 2 nets here that goes to the so sync 0 and sync 1. All right. So now we have our master output mostly, so it goes on the slave input. Messy. and those I don't need anymore. And I'm gonna place here a generic no ERC because I know that they are not needed. Those general purpose IOs, yeah, but wait a little bit, Cedric. I'm gonna place the coupling capacitors is just I'm just routing the main signals for now. Usually what I like to do, I place the main components, then I care about capacitors. So this is gonna be the next thing. Don't worry. All right. So those ferrite bits are not gonna need them anymore. And now we need to grab a isolated DC-DC converter. I already select one that I like it very much. So from Texas Instruments, so view portfolio, let me just open here. Isolated DC-DC solutions. Where is general purpose? What is, oh, okay. No, I am in the wrong place. Isolated, no. Book boost, no. Here. Yeah, we've integrated transformer because, yeah, I'm just lazy and I don't wanna. Okay, so I have 5 volts input, a current. I know that is a half an amp part that I had selected, and 1 and 1. View 2 parts. No. View to max. No, it's not showing the same part. Oh, I hate then when this happens. Guys, if you can share on Discord, where's the streaming link? How can I share this thing? Oh, share. I found the button. So copy. So let me just put there on general and post on Discord. So if people wanna join. Concurrent viewers, we have 4 people getting bored watching me. We have some error ports here. I don't care about it, so, but yeah, maybe I'm gonna use that reset thing, or maybe not. Yeah, for now, I don't care as well, because I'm gonna need another digital isolator only for it. So yeah, we have like the minimum required signals here to control the LAN and to synchronize. So yeah, anything is optional from here. Okay, so let me go back on my isolated DC-DC converters, phenomenal, outmax regulated outputs, view 7 parts, 1 watt. Let's put it by price. Oh, nice. Texas has some very interesting parts here. A new flyback DC-DC converter, 65 volts input. Yeah, input volts. It's a 0.75 amps of output, like $1. And yeah, it's brand new part. Oh, those DC-DC converters are so expensive. Maybe I made a mistake. Let me look around. I should be showing you guys, but yeah, I have. I would need to configure a different window. And not, let me see if I can do this. I don't. Nah, it is attached to Altium window and not to the display itself. So just hold a little bit. Yeah, like $5 for a DC converter module. No thanks. So let's go there to products, power management, DC switching regulators, step down, power modules. Let's see if it's this one. In 5 volts, let's say 5.5 volts. Yeah, 3.3. I'm pretty sure I found like a perfect part. I don't know, 300 milliamps. Yeah, but those are not isolated. Damn. Yeah, I guess I'm gonna need to implement a whole discrete isolated DC-DC converter. I'm pretty sure that was isolated what I saw. I can't be so crazy like this. And it was a nice price. It's at 17 volts. Was on my other operating system, so I can't just reboot the machine to see it because of the live stream. Let me see if I put on the OSMU discussion. No, I did not. Let me look a little bit. I didn't follow the discussion so much. What MSU was chosen for that control board? So we drop off the FPGA idea, and we got a dual core M2. So the new MSU is a STM32H745. So it's an Cortex M7 plus Cortex M4. We are gonna be using the M7 that's like way more performatic for the real-time calculation, and we're gonna be using the M4 for like EtherCAT communication orchestration, yeah, like display things like this. The M7 has double point FPU, so and like it runs at 408 megahertz. So yeah, so how much power I for what, for the DC converter, or like computational power? Yeah, so if you're talking about the MCU, basically we needed to interrupt, you know, at every single ADC acquisition. Ibrahim, yes, Marcus OSMU project, exactly. I am one of the collaborators on the project, and I'm working on the control module right now the control module takes like is responsible for the external world communication that we are using EtherCAT for real-time communication, and signal acquisition and signal synthesis. So the microcontroller basically, yeah. So in going back to the responsibility on our real-time control loop, we needed to acquire the samples at every single acquisition interruption. We needed to integrate the current that we acquired, so we can have like RMS current measurement in real time at 100 kilohertz per second. Then we needed to we need to do like all the PID calculation and any signal processing, whatever that we decided to do in this real-time loop. So this is the reason that I'm going as highest performance as possible on the MCU. I'm gonna post here the MCU STM 32.8 745 Z80. If any of you would like to play around, there's a Nucleo board for this MCU, and this was one of the reasons that I chose exactly this part number, because yeah, we can play around with a Nucleo board for it. Okay, for the DC-DC converter, I found something around half an amp. Of course, we don't need half an amp for it. I can open here the LAN 9252 data sheet, and I can confirm to you the maximum currency. But yeah, I always like to put at least 50% more on my power supply so I can work. So let's go there on the power connections, general description. Let's see the maximum current this puppy consumes. I'm pretty sure that is around like 150 milliamps. It's long time. I already read this data sheet like many times, and but yeah, it's been a while that I actually look into the power supply. Where is it? Microchip. I don't understand those manufacturers. They can't keep like an order. Most of manufacturers put like absolutely maximum ratings, like the first topic is on the document. Like Microchip, they have a lot of crap regarding registers that I don't care about now. And don't give me the information that I want. Power management registers, no, it's not what I need. Configuration straps, this is important, and I'm gonna need to review those. They should be okay, but we never know. Where is it? Where is it, Microchip? You're gonna make me scroll down 100 pages, really? For the most basic information. Let me just roll. There's so much information. Yeah, let me start from the bottom. Timing. Okay, power sequencing. Yeah, power sequencing, but no AC specifications. Transceiver characteristics, we are close. Low input level, variable I/O DC electrical characteristics. Let's see, millivolts, microamps, no. Millivolts, no, it's not here. No variable I/O electrical characteristics. Input buffer, millivolts, not on this page as well. No variable I/O electrical characteristics, no. Current consumption, here. Current consumption and power dissipation on page 310. Okay, device current. Device power with magnetics at 3.3. Okay, it's in, yeah, milliamps. So let's see the maximum value that I can find here, device current. General power down. Current measurements do not include power applied to the magnetics or the optional external LEDs. Okay, so the maximum value that I have here is 113 milliamps at 3.3 volts and magnetics current 82. So yeah, around 200 milliamps is gonna be our maximum current. So yeah, SN 5505B, it's a very nice IC. Let me see what you just posted there. Yeah, I love this this IC, but is not a little bit overkill, especially because I need a voltage regulator after it, right? And I really would like to stick with, well, but yeah, I guess it's just much easier to use the 6505. I was planning to use it on OSMU already, so since we are gonna use it anyways, I'm gonna place it. Pretty sure I had it designed on the library as well already. It's pretty quick. Projects. SN, where's my SN? I already designed this component in the past. I have many different libraries, so yeah, sometimes I just... thank you for the schematic, because I can just copy 6505B. Rectangle. Let's make like so. And pin 1. G1. 2 is the VCC. Oops. VCC 3 G2. Now 4 ground. Let's put here. 5 enable. Oh, clock. It has a synchronization clock. Which frequency this AC runs? It's actually very nice. It has a synchronization clock because then I can synchronize it if it works at 1 megahertz. I could synchronize with our master clock as well. I don't think so, because this is just a MOSFET job. Okay, you edit supplier link, add. Hello, purple, sing. Purple. Is it you, Mac? DigiKey. Which one I added first? Mouser, yes. DigiKey. So everyone's happy. Actually, I should look for link for TME. Hey, Mac. It's nice to see you around here. So, yeah, I'm gonna add footprint afterwards. Let's just, yeah, no. SN6505. Low noise 1 amp. Transformer drivers for isolated power supply. What is the difference between A and B? Package. SOT23. Oh, wonderful. I love SOT23.6. For me, it's one of the best footprints, and I don't have them on this library yet. So let's go there on OSMU PCB lib and use my preferred tool on Altium, that is where is my IDC compliant? What? No. What is my IDC compliant? Okay, I'm gonna. No, it's not this one. I don't like this one. No, 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 no. Where is my IDC compliant? Wizard? Why it disappeared? Okay, so I'm gonna create this package afterwards. Auto is panicking. I don't need it right now. So let's go there and use this. I'm gonna compile my integrated library again. And place. Where's my SN? Let's go out to compile. Is there any error? I hate when Altium starts doing this stuff shit. Like you compile the integrated library, it doesn't show you. Let me see if I go on schematic. Yeah, on the schematic directly, I can access it. So, okay. Let's make it this way. Let's see the live. So is this project open and accessible on GitHub or somewhere else? Yeah, so we have actually, it's good that you remember me about this, because we have a GitHub, is git.osmu.dev, and we didn't open it yet because we are deciding on the license that we would use for OSMU, but I think it's pretty much an agreement that meet license is gonna be suitable for the project. So yeah, I'm gonna put the link for you in the chat. For now, what we have been doing, we have been creating manually the users. But yeah, I'm gonna just update the license after this string for all the repositories to check if all of them have the license there, and then I'm gonna be open the Git server for everyone that actually wants to look into the project. We have many repositories for each one of the parts on the project. And if you want to collaborate, have a look around, and we're just curious, you can access there. For now, it's private. You need to request me a user. But from a few hours from now, when I finish this, I'm gonna go to the server and adjust the configurations to make it public. So git.osmu.dev is the repository. Okay, now the transformer. Let's see what Tesla is recommending here. Tesla, Texas, yeah. Mr. Elon Musk is getting on my brains. Just give me a transformer. Oh, 3.3. Okay, MPR. Oh. Input voltage. No, I don't want to step up. I want to step up, down. Just give me a nice part number. So. Recommended isolation transformer optimized for the device. Okay, 5 to 5, 5 to, where is 5.3.3, 100 milliamps. No, I need more. Isolation, okay, 2.5 kilovolts. Yeah, it's enough for OSMU. So let's use the 1 amp transformer because, yeah, this way I can use for the entire project. So some boom consolidation it's gonna be good. So let's see here. I have 5 to 3.3. So this is the transform from Worth Electronics. So let's go there on here first. Schematic library, add, this is gonna be our guy. That supplier links, let's see if this puppy is available, I hope so. Yeah, it's available on Mauser, and it's available on DigiKey. Okay. Designator T. And I don't like to show supplier links on the schematic. Sounds great. Yeah. Don't worry about this. I'm gonna post there for you as soon as possible. I release it. So let me just check the datasheet on this transformer. DigiKey 404Y. Worth Electronic. Okay, give me the datasheet. Oh, they're pretty. Okay, spec sheet. Yeah, I should have prepared like a second point thing here on OBS so you could follow me, guys. But yeah, sorry, this is my first time streaming, so OBS. So okay, so we have two beef filler windings, primary. So here we're gonna have pin number 1, and this is, yeah, basically there's no name. It's just 1, 2, and 3. No, I don't need it. 4, 5, 6. Just to be dump proof, I'm just gonna put here P5 volts. And secondary 3.3 volts. And I'm gonna place here 1 amp. Oh, 1 amp. That's not a variable. Now the footprint. This footprint I'm gonna need it just to create it. So I'm gonna call it the same. When I have very specific components like this, I just give the footprint name the component's name, because yeah. And this one this one I'm not gonna even bother. Well, actually I could use the footprint wizard. So let's see what I'm gonna use. Small multi-line package in freedom units, not imperialistic units. Okay, so my pad is gonna be 0.9. Where's the millimeters? Yeah. Okay, 0.96 millimeters. Why not 1? And 0.66 millimeters. Then the distance between them is 11.24, and the pitch is 2.54. Of course it is. And number of pins is 6, and the name is gonna be this. Hey, cool. Now we have our transformer without the 3D, because yeah, it's not gonna create concurrent viewers for. I wish I could actually like see who is online, especially for you guys that are like logged in with our Tuber accounts, to know you're a subscriber, not a subscriber. So it would be nice to have this kind of metric, but YouTube sucks. So anyway, so we should see, yeah, now we can see, and we don't have a 3D because, yeah, Altium is in a crisis moment right now. My IDC compliant footprint wizard is not working. All right, so control module. What I need to do, yeah, ecat. Now we grab our transformer. We grab our transformer. Yeah, so we do like, no, this is horrible. So is X. Yeah. Where is the schematic that was following in the OSMU discussion? Oh my gosh. Okay, so let me go there on Texas here. Okay, so VCC. Okay, makes sense because this is kind of like a half bridge thing. And yeah, so here I have already a port with our ground. So I'm gonna use this port and but this is, I had selected 3.3, so I'm gonna need the 5 volts line as well. Yeah, so 5 volts. I wanna use the 5 volts because the 3.3 there is it's like exclusive for the MCU. I'm really like separating well the rails because I wanna like kill the noise. So yeah, and the 5 volts is gonna be directly from the power supply. So is my main voltage source for the digital section, and from this 5 volts I derivate any power rails that I need on the digital section. For the analog section, we have totally different windings in the transformer, so it's totally completely isolated. So anyways, so now we can place here and yeah, and specify it. It's all right. Now enable needs to be, yeah, I guess 5 volts attached, right? If I make any mistake, you guys are gonna be happy to correct me. So now this clock thing, let me see what this clock thing needs. Yeah. Functional applications, timing. Okay, clock. This pin is used to run the device with external clock. Internally is pulled down to ground. If valid clock is not detected on this pin, the device shifts automatically to internal clock. All right, but how fast can be my clock? Let's try to find it. And specifications and in the 5th page. So good for you, Texas. Give me the important information in the beginning. Recommended operating conditions, electrical characteristics, clock pin, threshold, logic low, hysteresis, clock. Okay, so in the maximum, yeah, no, it's around like 500 kilohertz. So external clock frequency on clock pin, up to 1.6 megahertz. Great. So we are gonna synchronize our clock with our main clock source. So I'm gonna call this 1 megahertz Celica, and this is a input. Let me check the live stream right now to see. Yeah, thank you for the likes, guys. You see where I'm going? Yeah. I'm probably gonna move this isolation to a different sheet, but since I wanna do this like in a faster way, I'm just gonna keep here right now because yeah, it's AetherCAT responsibility, those I see. So yeah, it makes sense to keep in the same sheet as well if I want to. So now I'm gonna need some fast diodes, right? So let's see what Texas recommends. MBR0520L. I need to go out a little bit. Give me 2 minutes. Someone just left. Taxi go along with. Okay, guys, so I'm back. And so now I need to, let me see, I should have some diodes here as well. Already, not as well. Then English. Let me see, diode. No, this is just an LED, but I can just copy and what is this? Okay, interesting. Let me see what are the MBR 500 milliamps. So no, I can't get this one. So digikey.com English diodes. Not gonna get the. Let me put here in a different window. Diodes, rectifiers, single. Active, in stock, normally stocking. Those diodes don't need to be high voltage, so gonna get it like 16 to 50 volts, and I need at least 1 amp to 2 amps. Apply filters. And now we select the hotkey. And now we select for unit price, ascending. SMC diode, 50 volts. SOD 123. Okay, very common packages. So yeah, basically if we need replacement, then DigiKey has 27,000 parts. Oh no, but this is minimum quantity. Let me select here for one quantity. Yeah, if you select for a minimum price, where is that option to put the quantity on DigiKey? I'm pretty sure that they have this somewhere. More filters. Surface mount, apply. Where is that option that I can put like DigiKey minimum quantity? Okay, 20. SWOT and tree. Yeah, I kind of okay, let's put unit price. I'm gonna get the cheapest one here. And then I'm gonna search for this. Yeah, then they have for minimum quantity of 1. All right, so let's duplicate. So copy and paste. So this guy now is gonna be called DSS15UTR. Edit supplier links, and let's delete this guy. Delete this guy. Let's add our new Yeah, very cheap. Mouser doesn't have it. Nah, not really. I really like parts where I can actually find them in Mouser as well. Let's see this one if they have it. No, looks like this brand. Okay, on semiconductor, they're gonna have it. I'm pretty sure that Mouser has it. Yeah, this one everyone has. So yeah, it's your where's the G key? Oh, they have in stock what you're talking about. I can see in stock they have 13,000 parts. They have 16,000 parts. Anyways, yeah, and but everyone has this part, so I really not. Whatever. Okay, comment. Let's delete this comment designator and remove those flashy things. Because you're gonna be a boring diode. And you are black. And you are black as well. And this green goes away. Edo 603. Okay, so I'm gonna need to create so edit, and this puppy is a package do whatever. I'm gonna create this afterwards, but for now I don't care. MSS. Yeah. I hate supplier descriptions on. Let's remove this. And delete this. Yes. And yes. Yeah, cool. So now we don't have it. And now we have our Schottky diodes. I should have made the bendy. And from here I have our now ground. I'm working on an hierarchical way in Altium, so each one of the sheets has its own like net signals. If you're not using a port, they don't communicate between each other. Just telling people that don't know Altium. So yeah, I can put that ground here. It's gonna be a different ground from the other sheets. That's the advantage of using hierarchical. Okay, so now I have an unregulated output here. So now I need to go through a linear regulator, and let's see what Texas recommends. They're gonna recommend one of their parts, of course. But since I really don't care too much about, yeah, I'm just gonna grab any LDO. Volt reg 5 volts. TPS, yeah, let's see those. TPS is 76, low power, 150 milliamps. No, I need more. So since we are on Texas Instruments website, I'm gonna grab one of those there LDOs. Oh wait, I think I have 3.3 LDOs on the OSMU library. The reason for that is that I imported all the components from the reference design, and for sure we had cap, con, diode, fiducial. What is this? Ah, okay. A jumper. Max 232. Who uses this at this time? This is a Schmidt trigger. No. Inductor. Flash. Bunch of LTCs. Miscellaneous. Oh, okay. No. Miscellaneous. Microcontroller. Let me change this. Whatever. Oscillator, oscillator, oscillator. Transistor. Where is damn, I'm pretty sure that they had a regulator on the reference board. Not to be able to find it. Okay, whatever. So, oh yeah, let's go there on the low dropout regulators. And I'm gonna get like a 1 amp because yeah, this way I can use for other parts of the circuit. Parts consolidation, because it's horrible when you have a lot of like similar functionality parts, and for every one of them you have a different part numbers. Okay, low V in space grade LDOs. Yeah, so not really. So V in input 5 volts, V out 3.3, 1 amp. Fixed output, please, because I really don't want to use resistors to set the voltage. And now we select for price. Oh, they have like a $400 LTO. What? What is this? It's like with a super special package. Guys, look at this. This is crazy. Look at this. Anyways, just curious because yeah, it's base grade things. Low dropout with regulator with enable. Automotive 1 amp low IK, high PSRR. I like high PSRR. Yeah, it's an automotive, yeah, kind of expensive, adjustable output, fixed output. Yeah, like the difference on price between is like 1 cent to no from yeah 1 cent to 30 cents. Oh, it's a lot of difference. Let's see. Noise, noise. 60 microvolts RMS. Quiescent current, very low, 0.05 milliamps. PSSRR at 100 kilohertz, 50 dB only. Let me see this. Oh, low key high accuracy. Let's see this one. It's a little bit cheaper. Let's go to the product page. Basically 45 dB only PSSRR. Oh. $45. Yeah, 50. Yeah, actually the cheaper one has a higher PSSR. Let's go with this one. So our selected regulator is gonna be the TLV 1117 LV. It's basically a 1 cent part. This is too cheap to be true. 1 amp, yeah, 5.5 V out, yeah, 3.3. Great. So we come here, we add TLV, and this part uses so supplier link add, and this one everyone is gonna have because yeah, it's great. Oh, really? That one has stock? Let's see this one. Come on. That's a pretty common cheap part. Everyone should have it. Okay, this variants. They always have some variance thing that yeah, no one has that specific variant. So, okay, so we add Mauser. We add which one was? Is the DCYT. DCYT. And the G key. LV. Oh, no, wait. No, that's wrong. I need to get the full code. because yeah, those are fixed voltage. Edit supplier links. I'm pretty sure this is the 15 volts variant. Yeah, no, 1.5. So let me open the datasheet so I can see the full parts number. Okay, so it's gonna be LV33 something. Yeah. And no one has it. So, yeah, you know what? Forget it. I'm going to DigiKey. Sorry, Texas. It's not gonna be you. If they're cheapest, I have to turn the audio down. Are you on the speaker? Just get your headphones, man. I'm glad you are here this whole time. Voltage regulators linear. Part status active, positive, fixed, number of regulators 1, voltage input 5, and voltage output 3.3. 3.3. Why? 3.35. Oh no, here. That's what I need. In stock, normally stocking. Apply filters. Now we are talking. Okay, voltage input 5.5 max, voltage output 3.3. So now we select the cheapest one. Texas fucking instruments. But okay, I forgot to select the current. And I went to one map. Apply filter. Now it's gonna be diodes incorporate. Oh, the AP2114. I already used this in my projects in the past. I know this part well. Okay. So let's find it. Now tune. Yeah, and this part everyone has it. So great. This is a very nice regulator. And we can place the name here. No confusions. Yeah. Supplier links, I don't want to see them. Basically, this puppy only has 3 pins. So it's gonna have like one here, 2 here, 3 here. Let me see the data sheet for it. Oh, there's so many packages. Yeah, I think I went to the SOT 223. Sure that I went to the SOT 223. Let me see which one I got here. SOT 223. Okay. SOT 223. Let's see. Low noise regulator. Okay, for SOT. Wait. H or HA. There are variances on the package. HA is the one. Okay, so in the HA variant, this is very important. The pin 1 is voltage input. The pin 2 is ground that I personally like, and the pin 3 is the out. The reason that I personally like is because then you can connect your regulator tab directly on your ground plane. If you have the voltage output, then you can't. So yeah, you are losing the ability to use your ground plane to dissipate the heat from of course this like is really low power, but yeah, it's nice. I think it's nice when you can use the tab as your heatsink. Yeah, and actually it has like 68 dB of PSSR. Yeah, okay, they are measuring at 1 kilohertz, and Texas was measuring at 100 kilohertz, but yeah, it's good enough for Germany. All right, so now we can go there, compile our lib library, go away out to errors, and we can say, give me my regulator. Hey! And now we get our 3.3 label. And I know about the capacitors. I'm gonna place them soon. Now that we basically placed our first annotation on schematics. Yeah. Good. So we create our isolation for data signals. We created our isolated power supply for the ASIC and everything here. And now we can put some decoupling capacitors. As you can see here, I have 1 microfarad capacitors. And I'm gonna place one here in the input. So first thing that I'm gonna do is do this trick here. This input line has loads of capacitance, so yeah, I'm just gonna put 100 microfarads there, and now in the output I'm gonna place 100, and I'm gonna put one microfarad as well. Where are my 101 microfarad capacitors? I just need to find them. Yeah, I should, but no. So we just go to caps 100, 1 microfarad. Microfarad, and then we just place a ground here. And I also gonna place a capacitor in front of this regulator. Yeah. So I give some slack for this regulator here. Okay, and now we need to place 2 capacitors here. One goes to the isolated side, and we place where I'm gonna place it is, yeah, let's place here. Oh no. Oh, this is ugly. Let's make a proper job here. Yeah, and we just place a ground here. All right, now we can annotate. Everything is annotated. We have a few footprints to make, but yeah, since I'm probably gonna open my Altium 18 that I have installed here as well and trying there. But yeah, so for now, let's just try to import the footprints we already have. Import change. And it's gonna give me some errors. Don't show this again. No. Execute changes. Yeah, a lot of stuff. So first, this guy here. This guy is gonna speak with our. Why are you on this side? No, that's not correct. 15, 14. There's something wrong. Why some signals are on this side, other signals are no? They should be only one side being used. I'm gonna need to check that component. This is the reason that I like to make some changes on the schematic, import them, because then I have on my head, you know, how it's supposed to be. And if I see a net that looks weird, I found it immediately and I can correct, because otherwise, you know, I could just forget about this and then screw myself. Oh, this transformer is huge. I don't like it, but it's what we have for today. I really don't like this huge transformer. I think what I'm gonna make it is I don't like this transformer. It's too big. I'm gonna place. No, what you are doing. A bunch of capacitors. Okay, I'm gonna open my sheet on a different window so I can follow the schematic, so you guys are not gonna be able to see. 1, 2, 3, 4, 7. So what I did wrong here? Oh, I see. I use it for the ports the same names as my internal net names, and Auto does not like this. Yeah, now it's gonna for sync 0 and sync 1. I use the same part names as my net names, and Auto just uh, don't like this. It thinks it's the same. So I changed it to P underline sync, and now it's gonna work. Parts changes. Execute. Footprint not found. Yeah, so now it's correct. So this is our free side. This is gonna be our MCU side, and this capacitor it belongs to. Okay, U7, you stay here, and this. Let me select all my find similar components text. Okay, so I select all my texts, and I can define my height as 75, and I can place it through type Arial. Yeah, now all my fonts are exactly the same, and I can just place this capacitor here. Yeah, I needed to change my grid right now and put like 0.5 millimeter so I can proper position this capacitor. This you're gonna stay here for now. Let me place inside. Yeah, let me place this component inside the ROM. And great. Okay, that is the best we can do on this case. So let me grab this. Let me remember the capacitor. So this side is the C31. Yeah, C31, and the other side is the C30. Where's my C30? Oh, here, C30. So you go away, and you go away. Yeah, actually, no, that's not nice. I'm gonna place. I need to check which. Let me see here. Is it the 16? Okay, the 16 is the positive, so this is not correct. this should be here because I want to have a short path, root on root net. So okay, I want to have a short path to the VCC and not to ground, because the ground I'm gonna have a ground plane that is gonna give me a low inductance path. And yeah, I'm not gonna even bother to route there. And this is, I can't keep it so close because I have an isolation barrier in the middle of this component. Probably I'm gonna put some boards cut out on these critical parts, because yeah, to not have any leakage on the board in the future. All right, so let's see what we can do here. So this test point goes, why are you, yeah, this test point goes here for now. I think I can bring this this whole thing closer, like so. I have a few signals that are coming from this side, so yeah, maybe I'm gonna, no, I have this my analog region here, so yeah, I don't wanna keep this so close. Probably maybe I'm gonna rotate this MCU. I need to think about it if I'm gonna keep this orientation right now, because I moved the EtherCAT from this side to the right side, because yeah, the port orientation. So I'm maybe gonna change this. Baby can stay like so. So we have a nice alignment with the other connector. Ah, I'm getting tired. Yeah, and this transformer, ideally this position is better, because then I can have like a clear barrier here. So my input here is on, let me see. Yeah, 6, 5, and 4 are the outputs. So I need to rotate this component like so. And then I can actually place, yeah, I'm not comfortable because it's very close with the IDC connector here. I think I'm gonna reorganize this thing. Like this is kind of temporary layout, you know, because yeah, I reoriented the ASIC here, so yeah, I have some empty space here. Yeah, so probably I'm gonna unroute this component and shift this ASIC so I can have more real estate here, and or I can make this ASIC lower, and I can place the power supply on the top region, like here, around here. I guess this is gonna be the best strategy, and I guess I'm gonna make this already right now, like so. I can even bring a little bit more. Yeah, and now we should have, yeah, now we have plenty of space. Yeah, it's a little bit tight yet, so I'm gonna bring, yeah, and also I can like remove that component from there, so I can bring this as well. to this direction. And now we have our space here for the SN 6505 controller, and we have our transformer here. So we have a more or less isolation barrier on this corner, and here I can basically come here on the top overlay and create a keep out zone. Yeah, like so. So that's gonna be our different voltage potential region. All right. Since my IDC thing's not working right now, footprint generator, I need to figure out what is going on, and I'm not sure because OBS is attached to Altium right now for one of the windows. I'm not sure what happens when I close the application. So guys, I'm gonna shut down the live stream, and yeah, so next week we have a other live stream. I'm gonna be working on the power amplifier. So Hasvan have been working on the Hughes power amplifier, and he promised me that he's gonna finish the schematic with the up-to-date components for it this week. So until Friday, Saturday, we should have the schematic. So I am not gonna need to create any components, and we're just gonna route the PCB. So we're gonna I'm gonna schedule a new live stream for next Saturday, and we are gonna go through the whole PCB routing for the Hughes amplifier with the up-to-date SMT components. I think it's gonna be great. For the control module, yeah, I need to keep creating components, you know, go back and forth looking schematics. So it's a really like intricate problem. And yeah, if you design ports, you know what I'm talking about. So it takes a lot of time. So it's not as dynamic I would like to be. But next week we're gonna do another live stream, and it's gonna be great because we're gonna have the schematic, and we're gonna plant the PCB together. I'm gonna show you the schematic. We're gonna look into the different sections. There's, for example, the output sections that needs to have very low inductance. So we're gonna leverage, for example, the power planes, and we have the feedback loop that is very sensitive to interference. We're gonna think about the strategy that we're gonna use there. So check next week, guys. Keep a look. I'm gonna schedule with antecedence, probably on Friday. And as soon I get the schematic on hand, I'm gonna book the live stream on YouTube. So thank you guys to join me together, and I see you next week.